Last time we took a look at section 12.4, similar triangles and other similar figures. And we had stopped at taking a look at, or we were about to take a look at properties of proportions. We've got quite a few properties of proportions here that we're going to look at. The first one talks, and they all talk about parallel sides to a triangle is what they're really strongly reflecting. If a line parallel to one side of a triangle intersects the other sides, then it divides those into proportional segments. Okay, so now I know some of you have taken proportional statistical reasoning. So proportion is just A equals, an equation of ratios. Okay, two fractions that are equal. So if you're taking a look at this one right here, they're saying that the, let me read what I said it correctly. One side of a triangle intersects, it divides the sides into proportional segments. So, let me get my white. The sides of the top triangle, x to z, would be proportional to the sides below, which are x plus y to z plus w, the whole side lengths. Okay, so that's the proportionality that this is talking about. You end up with these proportional segments within your triangles. Not only that, but the reverse is true as well. If a line divides the two sides into proportional segments, then the line's parallel. This is fantastic because it's like an if and only if statement. You get it from both directions. If you know it's parallel, then you know you have the proportional sides. If you know you have the proportional sides, then you know it's parallel. And the last proportionality statement is even more specific. It actually talks about congruence. If parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on any transversal. So in other words, these parallel lines, if they are all spaced equally apart, that's what they're describing, then if you cut through with this transversal AD, you end up with all these congruent segments, then all the segments on any line cutting through that line, those parallel lines, will cut off congruent segments. Okay, so even in my picture, if I decided that I was going to draw into my picture another one right here, those would all be cut off into congruent little segments, and this one cut off into congruent segments. Okay, any transversal that cuts through will cut into congruent segments. And we actually need that fact in order to be able to do our last construction. Our last construction says to divide a given segment into congruent parts. So we're going to take the segment that's on your paper and you're going to divide it into congruent parts. And notice it doesn't say how many because you could do it for however many and then it would be in the same fashion. Okay, so we're going to do that next. All right, so in this dividing the congruent segment, the whole idea of that construction was this particular fact about proportionality and parallel lines. Was that when we have these parallel lines, if they cut off congruent segments along one transversal, they cut it off along any transversal. So that's what we were using in that construction. A midsegment. So a midsegment is a segment of a triangle connecting the midpoints of two sides of the triangle. So this is a midpoint, M. That's why you see the two blue marks here. And then this is another midpoint, N, and you see these two side lengths, or the lengths of those are the same. What do you think you could say about that midsegment? What does it appear? This is okay. So this is Morgan is an example where I'm asking you to guess. You were saying like before you were looking at one where you were like it just looked like something, right? What does this look like would be true to you? What do you think you could say about these different pieces of information about this picture? Okay, so you believe that the image at the bottom is a trapezoid, okay? What has to be true about a trapezoid? Do you remember the definition of trapezoid?
It just has to have one set of parallel lines.
Okay, so what you're really saying when you're looking at that is you believe that the lines are parallel. And that is one fact that's true. So segment MN is parallel to segment AC. So MN is parallel, that's that double line, to, what did I call it? AC. So the mid-segment is parallel to the third side. I mean, generally speaking, that's what this fact is. What else do you think you can say about the relationship between MN and AC? Can you be more specific, Brendan? Do you know what the proportion is? Brendan's guess was they're proportional, and he's right. But there's a very specific proportion that they have. Can anybody see what that proportion must be? Yeah, it's 1 to 2. Exactly. So the mid-segment is half as long as the third side. So I should have put segment markers here. I'm sorry about that. The segment MN itself is actually 1/2 of the length of AC. It's half as long. And the reason, of course, is because that triangle at the top is similar to the bigger triangle, right? But the sides at the top are half the length of the bigger triangle sides. So the third side would have that relationship as well. That's all this is saying. In particular, if a line bisects one side of a triangle then and is parallel to the second side, the triangles are similar. They've got these proportional side lengths. They've got the angle at the top the same, so that side angle side that we did before holds for similarity. We have similar triangles. And we actually use that fact, and we will use that fact in a lot of measurements for mathematics with triangles. One more piece of information before we're going to do our last example of the section. And that piece of information is about the word median. A median is a segment of a triangle connecting the vertex to the midpoint of the opposite side. Okay, so if we found the midpoints of the three sides and we connected the midpoint here, F, with the opposite vertex B, that would be called a median. So there's 3 of them, right? There would be 3 medians because there's 3 vertices. And those medians do all, in fact, intersect at one point. That point is called the centroid. Another word for centroid is center of gravity. Center of gravity is more general. You can use that for any shape. Okay, so like a square has a center of gravity, a circle, an ellipse, whatever two-dimensional shape you want. All of them have a center of gravity. Centroid is specific to a triangle. And you want to think of it like a balance point. So have any of you guys seen Nicolas Cage, the second one? National Treasure 2. Yeah, National Treasure 2. And they get to a point where they are inside of Mount Rushmore, and they're standing on something that's sort of like two-dimensional, and they're trying to balance it on a single point. That's what this is talking about. That's the balancing point. It's the point that if you could actually take a two-dimensional object and set it on top of, like the basketball players, right? You set it on top of one single point, it would actually just stay there in perfect balance. That's what a centroid is. A centroid also divides each median in the ratio of 1 to 2. So if you take a look right here, if this is length 1, this is twice as long. So the distance from the median to the side is the length 1, and the distance back to the vertex is of length 2. So whatever those numbers are, they're in the ratio of 1 to 2. All right. Similar triangles are super, super helpful for measuring things that you would otherwise not be able to measure. And here's a very good example of one. I'm not going to climb the tree to measure the top of the tree. If you really want to, you can. But if I want to measure the tree or the flagpole or whatever, I'm not climbing to the top of it. You can use shadows to do that and similar triangles. So I'm going to show you how to do that. All right, so we've got our little guy or girl. I think it's actually a girl because I think she's wearing a skirt. She's standing right here, and it tells us she's 150 centimeters tall. And then it tells us that this shadow is cast. And so they're actually measuring her shadow to be 3 meters from her to the end. Does everybody see that okay? And she's standing in such a way that her shadow is ending at the same point that the tree's shadow is ending. And you can imagine going out and doing that, right? You just walk until your shadow meets up with the edge of the tree. So the tree's behind you, and the sun's coming down, and your shadow's out here ending, and so's the tree. Can you picture it happening in real life? Okay, good. All right, so this creates similar triangles. Why are there similar triangles here? Well, There's several reasons. One reason is the angle is the same, right? You've got the same angle down here at the bottom. Yeah? The other thing is that you've got the same angle because you're standing perpendicular to the ground, right? 90-degree angle. You're not going like, you can't do it without falling. You're not doing this, right? No. And neither is the tree. At least presumably the tree is standing at a 90-degree angle. 2 angles is all it takes to have similar triangles, right? 2 angles, and you have that. So these are similar triangles. So what is the ratio I could set up? Well, we have to take a look at the triangles individually. So here's my first triangle, the triangle of the young lady. So what are the side lengths ratio, and you can do it in any order, what would be a ratio of the values that we know in this triangle? 150 to what? To 300. Let's just do 3. We can do centimeters to meters, no problem. Okay, we do not have to convert. We will convert later, but there's no reason to here for anything. 150 centimeters to 3 meters. Equals. Now we're going to do the ratio of the tree itself. So here's my tree. The height of the tree is what I don't know, right? And the height is what I put on top of the other piece. So this is my x. Will it be over 15? That's a great question. It'll be over 18. Why 18, Brendan?
Because the shadow of the tree includes the shadow.
Yeah, you got to include the shadow that goes all the way past the young lady because it's actually part of the tree's shadow as well. Now, if you were standing next to the tree, it may not look like that. You might actually have a separate value, and that's okay. But this one actually measures it with it the same. And this, of course, will still be centimeters on top, and it'll be meters on bottom. So the centimeters are in the same place, the meters are in the same place. It's lining up. All right, so let's take a look. We can cross multiply. I know it sort of feels a little bit funny to multiply the centimeters and the meters together, but it all comes out in the wash, not to worry. So I have 3x equals 150 times 18. What is that? 2,700. Good. And then what do I need to do? Divide by 3. So what is 2,700 divided by 3? 900. And I do need some units on this. Yeah, be careful. This is centimeters because that's how the girl's height was measured. Centimeters. So the tree is 900 centimeters tall. I mean, you might not actually report it that way in real life. I mean, you might turn it into meters because it makes more sense, but that is the same measurement. Any questions on that one? All right.